Hello, everyone. We're going to take a bit of a switch from our ESG panels to resources. I'd like to introduce one of our keynote speakers at our 51st annual Yukon Geoscience Farm and Trade Show, Travis Pettigrew. He will be doing an overview of small modular nuclear reactors and their application for mining. He is an operations research analyst with the Canadian Nuclear Laboratories. Thank you.
All right, thank you, everybody. There we go. Okay, so yeah, my name's Travis. Thanks for the invite, everybody. It's an honor to come here and talk to you about energy and one of the exciting possibilities that are upcoming in Canada. So I'm going to give you an overview of the small modular reactor technology and some application for mining. So first, I'm going to go through some very high-level basics on nuclear and discuss a bit of the common terminology you'll hear, especially terms like small modular reactors. I'll then go into kind of a high-level view of the energy landscape in Canada, give you a brief introduction to who CNL is and what we do, as well as look at some case study work kind of at a high level to give you an idea of what sorts of things we're working on. Okay, so first the basics. Water-cooled technology is the most prevalent in Canada, or in the world, actually. Most of the reactors are in this category that are in operation today. So they're generally categorized into kind of three main buckets, where we have boiling water reactors, pressurized water reactors, and pressurized heavy water reactors. And in Canada, we have that last category exclusively in terms of commercial units, and they're called the CANDU reactor technology. As of February of this year, there's been about 438 total reactors operating worldwide. So it's quite prevalent, and this accounts for about 10% of the global electricity. So the first term I'll talk about is advanced reactors. This is one you'll hear quite often. This really represents a category of the next generation of reactors. A lot of them are non-water cooled kind of designs. And these represent new generation that's built upon things like advances in nuclear physics, in material science, and in system engineering. So you'll see some examples out there like high temperature gas cooled reactors, liquid metal cooled, and molten salt are some of the more prevalent ones, but there's others as well. Yeah, so these kind of designs typically take advantage of innovative fuels, high temperature for, sometimes geared more towards industry, high temperature industry requirements, but also the higher temperature can help with the conversion efficiency for electricity. A lot of them use advanced fuels and fuel cycles. There's waste burners, which actually will have the potential to use spent nuclear fuel from more conventional water-cooled reactors. And there's even designs out there for breeders where they can actually produce more fissile material than they consume during operation. All right, on to probably the biggest buzzword in the industry right now, small modular reactors, or we like to call them SMRs, because we like our acronyms in the nuclear world. So the first thing you'll notice is that small is a relative term. You'll see here that generally it's categorized as anything less than 300 megawatts electric, all the way down to about 1 megawatt would be kind of the lower limit. And they're made for modularity. So the thinking here is to bring a lot of the complex manufacturing into more of an industrial setting, bring it indoors so that we can factory fabricate these modules. And instead of having these long drawn-out construction timelines in the field, you instead are assembling, doing simpler assembly of the modules. One particular feature that you'll see in a lot of these designs is the inclusion of inherent and passive safety systems. So the industry is really moving away from reliance on active safety systems such as pumps to have emergency water flow for cooling, these sorts of things. So it's really moving away from needing electricity and other power sources to ensure safety. All right, so with that basic terminology out of the way, we'll move on to the more broad energy landscape in Canada. So I think everyone seems to be aware from the talks I've heard that reaching this net zero goal is going to be a huge challenge. So the first thing that you'll see most people talk about is the large-scale electrification. So we're looking at maybe 2 to 3 times the electricity demand by 2050. So this really speaks to how large of a problem, because not only are we trying to replace existing fossil fuel generation, but we also need to account for this huge demand growth in a short amount of time. So that's very significant. And in light of this, the scale and the complexity and the timeline required to deploy more energy, the old kind of argument of renewables versus nuclear versus other clean tech, this argument is really outdated, and it's not helpful going forward. It's really more of an all options approach that we need to adopt. There's not one technology out there that's going to get us there. So why nuclear? Like anything, there's pros and cons, and it's important to really get the context and understand both sides of the coin. So you'll see in the graph on the top right is life cycle CO2 emissions intensity by the generating technology. So this will be in grams of CO2 per kilowatt hour. And you can see that nuclear is among the very best in terms of emission intensity, very closely aligned with onshore wind projects, and less than even offshore wind and solar PV. On the bottom left, this is one metric that's used to look at the safety of plants. So you can see in terms of safety record, this metric is in mortality rate by generating type. So the deaths per year per terawatt hour generated. And you can see that nuclear is at the very bottom, which it represents the very best in performance in this metrics. So in many cases, it's much lower by orders of magnitude than a lot of the other conventional generating technologies. There's other advantages, including the high energy density of nuclear, the clean heat that it can produce, the reliability and dispatchability, which is an important part of the energy mix anywhere, whether it's on-grid or off-grid. It's independent of weather and geography, so in a time where climate change is going to start affecting our local climates, this can be a very resilient technology for that. And it can also enhance energy security, which is an important topic, especially in the last few years. And as I mentioned, it's not perfect. So you have to take the good with the bad and weigh the benefits versus the drawbacks. So I'll speak to a few of the major the drawbacks. It's a high capital intensive technology. So really a lot of the costs are upfront, and you need a longer duration of operation to really recover your costs. And in some cases, SMRs will help. It's a smaller reactor, so the capital investment will be smaller, but it's still significant. Also, in terms of deployment and construction, the industry has this historical problem with cost overruns and delays, project delays in construction. And this, of course, will not be helped by the fact that we haven't built any new nuclear in more than 40 years in the country. So this is a pretty common problem throughout the world in the nuclear space. The SMR developers are really looking to try to constrain these problems, deal with them in design. So that's part of the reason why this modular construction is really a benefit. There's also the, of course, long-term waste management requirement. So this is, of course, an important thing to consider. Although in the nuclear industry, we kind of like to look at it in maybe an opposite way, where we're one of the few industries that actually account for our waste instead of sending it up into the environment. But this is still a very important topic that we need to consider. and of course public perception. For many years, nuclear has been almost like a dirty word where people didn't want to talk about it. And I'm happy to see there's been a big public shift in the last few years, and I've seen it here. Many people are interested in asking questions, so that's a very good sign. Okay, so quickly, let's look at the European perspective just to get some context on decarbonization efforts. So in 2019, France and Germany had several similar renewables penetration, almost at 20%. So they're quite aligned in terms of the renewable rollout, but there's a very drastic difference in their approach to nuclear energy. So France has embraced nuclear, and more than 60%, probably in the 60 to 70% range of their electricity comes from their nuclear fleet, whereas Germany has decided to phase out nuclear completely. And as a result, they're seeing much more dependence on fossil fuels instead of reduced dependence. And in fact, they actually rely on a pretty high percentage of coal for their energy. On the top right, you can see the European electricity carbon intensity in terms of grams per kilowatt hour. So I'm not sure you'll be able to read it, but Germany is circled in red and France is circled in green. So you can see here that Germany actually has a much higher carbon intensity for their electricity compared to France. And in fact, it's something like 6.5 times that of France. And perhaps embarrassingly, they're actually above the European Union average for carbon intensity, despite all their efforts and time spent trying to decarbonize. The graph on the bottom right is for average consumer electricity price. So this is in euros per kilowatt hour. For the same year. And you can see here that German households paid on average about 2 euro cents per kilowatt hour more than that in France. And again, they're above the average in the EU. So actually, before I move on, I just want to highlight that, what do we learn from this experience? And to me, the biggest factor here is in the need for clean, firm power. So it's really a must if we're serious about decarbonizing, especially deep decarbonization. So these sorts of technologies need to be part of the discussion. And we can look at another example of a decarbonization effort that's a bit closer to home. So the province of Ontario was able to eliminate about a third of their, or just over a third of their emissions within an 8-year time period from 2007 to 2015. So this is a pretty significant decarbonization initiative, and it was really accomplished by the phase out of coal, all the coal generation in Ontario, and replacement of that capacity largely with nuclear and renewables. So nuclear was increased about 7%, and renewables about 8%. A large portion of that was wind turbine systems. So this can be a winning formula. Okay, so on to SMR development in Canada. So I'll talk a bit about the progress. There's an MOU that's been signed by a number of provinces, including Alberta, Saskatchewan, Ontario, and New Brunswick. And this may expand in the near future to other provinces and territories that are interested in being part of the conversation with this development. They've settled on kind of 3 main streams for development for SMRs. The first is the on-grid application around the 300 megawatt scale. These were focused on near-term deployments, so they're more based on traditional technologies, water-cooled technologies. And the GE Hitachi BWRX 300 was selected by Ontario Power Generation and Sask Power as the reactor of choice in those jurisdictions. So in Darlington, they're looking to site 4 units, with the first demonstration to be online in the 2028 timeframe. And Saskatchewan is looking to follow their lead with up to 4 units. So stream number 2 is advanced reactors, so more non-water cooled technologies. New Brunswick Power is really leading the way on this grouping. And they've selected two options here: the ARC 100 and Moltex SSR waste burner reactor. So These are the two technologies they're looking to bring and site at Point Lepreau, which is an existing nuclear station. This is pretty typical. The first of demonstration reactors are really looking to be sited at existing nuclear sites, which should help with regulation and these sorts of things. And as well in Stream 3, this one's geared more towards off-grid, remote communities and remote industries such as the mining industry. And these are targeted for about a 15 megawatt electric or less reactor size. So the leader in terms of deployment is a company called GFP, Global First Power. And this is actually a collaboration between two companies, Ontario Power Generation and Ultrasafe Nuclear Corporation. So USNC has aligned themselves with one of the biggest owner-operators of electricity generation in the province. So they're looking at the late 2020s for deployment, and the deployment is slated for Chalk River Laboratories, which is one of the CNL managed sites. All right, and one more development in the nuclear space. It's not so much SMR related, but it kind of gives you an idea for the way of thinking in the last few years on new nuclear. The Bruce Power site has announced that they're going to do some pre-development work on up to 4,800 megawatts of new capacity. So based on the size, that's I'm sure lining up to be a more conventional build as opposed to a smaller reactor. Okay, so CNL, we're kind of leading the way in terms of Stream 3 deployments, so I thought it made sense to give you a very brief introduction to who we are and what we do. So here, we're Canada's national nuclear lab, and we have three strategic priorities. The first is to restore and protect the environment. So work in this space is things like environmental assessment, remediation, and management of the government-owned sites. Nuclear sites. The second is clean energy for today and tomorrow. So this is a lot of the work is to support the existing nuclear fleets, both in Canada and abroad, as well as support development of new technologies such as advanced reactors and SMRs. And we're particularly helping out in areas such as advanced fuels and materials, safety and security, as well as hydrogen sciences. And the third priority is the improvement of the health of Canadians. So we have a long history of medical isotope development and production for things like medical imaging and cancer treatments. And the latest focus in the company right now is in targeted alpha therapy. So this is a promising new cancer treatment that looks to target the cancerous cells in the body and leave the healthy cells more intact. So more targeted treatment for cancer, and it uses an isotope called actinium. Okay, so as Canada's national nuclear lab, we're responsible for supporting environmental stewardship, clean energy, and public health. And we're really mandated to deliver the science and research required to inform government policy. And we do a lot of work for a wide number of the federal departments. A lot of our work is for the Canadian Nuclear Safety Commission, which is the nuclear regulator in Canada. We don't design or sell anything. We're not in the business of producing the reactor designs. So you can think of us more as a knowledgeable third party, where we provide science-based evidence and some impartial evaluations have been done for some customers. Okay, so we're a national lab, but there's also some unique features that differentiate us a bit from the other nuclear labs around the world. So we maintain some compliance in some of the management system and quality programs, as well as we have the ability to enter into commercial contracts where work done as part of the contracts, the IP belongs to the customer. So this ability to work directly with industry is very attractive for us, and we can direct our own investment priorities as well. So I'll talk a bit about just maybe a few of the more relevant initiatives we have going on. So this is called the Canadian Nuclear Research Initiative, or CNRI. So this is the idea is it's a collaborative project that we will do with SMR developers. So they get access to our site for helping to further their designs. And in return, we kind of are able to build up capabilities in these new reactor technologies to help us inform the government on the different technologies and safety. So we've worked with a number of the developers, including USNC, Moltex, Terrestrial Energy, among others, and we've even done a bit of work in the fusion space. The latest call for proposals for this is actually currently open, so it ends in mid-December. All right, another one of the exciting initiatives we have is what we call the CEDAR initiative. Again, another acronym. Sorry about that. It stands for Clean Energy Demonstration, Innovation, and Research. So although we're doing work in clean energy right now, it's more focused on lab scale experiments and modeling. This really represents our long-term vision to have a clean energy park at Chalk River Labs. So we're already siting or going to be siting an SMR technology there. So we really want to leverage that to be able to do more research and work on integration of clean technologies, which I think is really the future. How do you integrate wind, solar, energy storage, and nuclear together? And we really want to focus not just on the energy production, but using it for something meaningful. So solving the actual problems we have in Canada and seeing how best to do that. So potentially this could be what does it look like to use the heat directly for industry to decarbonize steel making, or how would you use it for mining most effectively, or even more basic human rights like food, fresh fruit and vegetables, and maybe using the heat for a greenhouse up north. So these sorts of things are what we're interested in. And we're really hoping this is a place where we can bring together government and academia and industry, as well as foster these collaborations with Indigenous groups and the public. Okay, so with that, I'm going to move on to the last section of my talk. It's going to be focused on some work we did as part of the Federal Nuclear Science and Technology portfolio, so work funded by the federal government, and this is in particular SMRs for green mining. So we selected a few case study sites to try to help us work through what a clean energy system might look like in the future. So we selected an open pit diamond mine in Northern Ontario, as well as an underground base metal mine in the Northwest Territories. So this analysis was done assuming a $170 per ton carbon price, which is in line with the longer term goals of the federal government. We use publicly available data for this work. So you can see the line in black represents the average monthly requirements for the site, and from that we extrapolated hourly demand. So in this case, you can see that the electricity demand is fairly constant throughout the year. So there's of course some fluctuation, but it's more constant in nature, and the heat, as you'd expect, being in more northerly locations, it's much more variable in terms of daily, but also seasonal fluctuations. And this creates kind of an interesting problem for electricity generation, because electricity is really an on-demand kind of a product. You need to generate exactly the right amount at exactly the right time. So once you electrify a site, this variation that was usually in heat actually becomes a problem in the electrical grid. So now you have the potential of having to oversize your electricity infrastructure so that you can meet the peaks, whereas in the summer now your system is oversized and you don't need as much energy. So for this analysis, we used a model we've created, a hybrid energy system optimization model. So the idea here is it's a techno-economic model. It's based on mathematical optimization. We really saw a need in the market for these kind of tools to basically look at all the different technology options and see how you can combine them to make the best system possible. And most of the modeling tools out there in industry generally, they were just completely leaving nuclear out of the picture. So we really saw a need to have this as something in our portfolio. So it considers up to 13 generating technologies, some fossil fuel and some clean energy tech, so that you can do some comparisons with baseline sites and near zero sites. It also considers up to 4 storage systems. So you input things like what technologies you're interested in studying, the respective technical and economic parameters of each technology, and your end use demand. And what a little output is the optimal energy mix for the site and for that demand. So here's a look at the baseline system. So you can see the system is characterized by being very segregated. So heat and electricity and vehicle fuel are all dealt with separately. But they all have one common denominator, is that they're all, in this case, derived from diesel, but more generally fossil fuels. In one of the case studies, we assumed wind turbines were installed to help offset some diesel usage and emissions on site, which is going to be probably a pretty likely scenario once SMRs are actually available commercially on the market. Another option for decarbonization is waste heat recovery from the diesel generation. These steps can be effective in reducing emissions, but they won't be able to decarbonize a site completely, or even produce a deep decarbonization on their own. So you really need something more base load. So here's one example of what a near zero emissions configuration might look like. And we decided to focus on near zero and not net zero. Mostly because of these variations, these seasonal variations in energy that you're going to see with fully electrified heating systems. So fossil fuels are very good at being cheap to buy, and then you pay for them as you use the fuel. Whereas nuclear being capital intensive, you really need to apply it to scenarios where you're going to get the payback over time. So you really need to have it running at fairly high capacity factors. So reactors aren't good at things like peaking plants or as backup generation. So we really see, unfortunately, that fossil fuels might be part of the picture for the foreseeable future until maybe there's more developments in energy storage technologies or alternative peaking plants, potentially hydrogen. So these systems are much more highly integrated, which also creates more of a challenge for the controls. All the energy streams are made by a common system, so your heat, electricity, and your vehicle fuel is all by the same system. You see as well here the huge increase in electricity demand. So that's something that's a little more difficult to deal with as well. But we found that these deep decarbonization can be effective, so it's definitely achievable. And what we found in this work was that you can reduce, by up to 90 to 97% the emissions. So that's a huge decrease in emissions. Which is especially impressive when you consider that one of the baseline scenarios that we selected was actually one that actually had some decarbonization efforts in place. One of the interesting parts of this work related to the vehicle fleet analysis. So we looked at the haul truck fleet, and we considered 2 vehicle types, battery electric and hydrogen fuel cell electric vehicles. So in terms of desirable features for your fleet, you'd want one that's energy efficient, that has short refuel or recharge cycles, and it has minimal fleet size impacts and associated, minimizing infrastructure impacts. So what we found in this work is that battery electric vehicles are quite efficient in terms of energy. You produce the electricity and then you use it directly in the vehicle, and it has a very high efficiency in electricity usage. The downside for the hydrogen vehicles is that you require a whole lot more electricity and energy more generally to produce the hydrogen, and you really get hurt by the efficiency losses in the system. So, at a basic level, you're producing from heat to electricity, and then you're converting electricity to hydrogen, which has a loss associated with it. And then once it's in the vehicle, it's actually reconverting that hydrogen back to electricity to drive the vehicle. So these efficiency losses add up after a while. All right, and you can see in the table that the battery electric vehicle fleet actually required almost double the amount of haul trucks in order to achieve the same haulage. So this could have some very serious impacts on your mine site design. That's something that's not really in our capabilities to assess, but we're hoping that some companies in industry are interested in this kind of analysis to help out with that quantification of that. So as it turns out, the rest of these desirable features I mentioned, hydrogen is actually quite good at. So these hydrogen trucks would operate much more similarly to diesel. So it has less impact in terms of the fleet size, less impact in terms of the mine infrastructure to accommodate more vehicles, as well as they have the short refuel cycles. So what we see is really these fleet analysis may end up being site specific, and it involves trade-offs as to the technology that's selected. Okay, just a brief recap on some of our results. As I mentioned, deep decarbonization is achievable with these technologies. Smaller and more SMR units might be preferable to having just one large unit on site for a few reasons, to more readily fit the demand of the system, to able to accommodate load growth going forward. So you can imagine if as the mine progresses along its journey, that you might add a unit, an SMR, as you go, and also in the perspective of reducing contingency reserves. So you're going to have to take things down for maintenance every now and then. So really thinking about what reserves you need and the size of the reserves can be impacted by the unit size. And as I mentioned, vehicle fleet decarbonization is a complex question, and it's going to involve a lot of trade-offs, and so that's going to take some more work to kind of figure out. The net present cost of the energy system itself is looking pretty favorable, especially with that carbon price in place. But keep in mind that the graph here is actually only for the energy system, and the vehicle fleet impacts aren't captured in this yet. So more expensive vehicles, potentially more numbers of vehicles, and more infrastructure to accommodate the increased traffic is going to be a big factor going forward. So I only have a couple minutes left, so I'm not going to go through this in any detail, but there's lots of other case studies that we've done, notably the top one there for remote mining that we did for OPG and a group named Merarco, they're a not-for-profit research firm in the mining space, and they had a mining partner that didn't want to be named as part of the work. So we actually got to work with it kind of indirectly with a mine site with real data. Also, the future interests for us really are about trying to get partnerships and to collaborate on work. So trying to get more involved with industry in trying to help solve problems. We're not the experts in your industry, so trying to come up with meaningful results is really going to be a kind of a partnership. And as well as we're working on a number of university partnerships to really try to further not just nuclear but clean energy systems in general. So a lot of universities have been doing a lot of good work on renewables and storage and other things. So we really see this as an opportunity to kind of develop more of a national network of labs mindset. So let's work on these problems together. And as well, we really want to get into the Indigenous and public partnerships and really have this work going on where we can form these jobs together and do this analysis and learning together. So with that, thanks very much for having me. It was a pleasure to be here, and I'll be happy to take any questions if there are any. All right, I see some over here. Hey, who wants to go first?
What's that, just the rough average cost of the 15 megawatt?
6.
300 megawatt?
Yeah, so cost, it's a cost question. Cost data is very challenging. A lot of the proponents that are selling these reactors are holding costs very close to the chest. And unfortunately, like the financing side of it is not my area of expertise, so I'm not sure exactly how much they're going to cost. But I do know the first ones are going to be much more expensive than the following ones. Just getting those learnings and really what they're relying on is these economies of multiples. So once you start building a kind of a fleet of any kind of reactor, that's where you're going to see the savings. But unfortunately, I can't give you a number. Sorry.
Fascinating presentation. Thank you very much. On the cost slide, I was surprised to see how competitive the small modular reactor options were. But on the baseline of diesel, how much of that cost was the carbon tax versus the diesel itself?
Both were significant at the $170 per ton price. So yeah, they both represented a big chunk of the cost there. Yeah.
Okay, thanks. Enjoyed your talk very much. Can you talk a little bit about whether a design consideration of SMRs, like in the Yukon, we're probably looking more at the 5 to 50 megawatt size. Whether a design consideration is their ability to be relocated, in particular for off-grid mines that don't have a 50-year life. The average life of Yukon mines probably 10 years. So can they be relocated, modular design, but can they be unpackaged and shipped to a different site?
Right. Yeah, that's a great question. And of course, you know, inherent in this question is the fact that you need that long payback period to make the technology make sense. There are some that are looking at developing reactors for kind of redeployment, but I think that's more of a niche. I'm not sure how easily these will be relocatable from site to site. I think the Department of Defense in a few countries are actually looking at reactor technology. So this is kind of where I think the big push will be for being able to relocate them easily.
Yeah, right here. I guess a question for me is in terms of, is this something that you can consider things going in parallel so that you can actually ramp up? So for instance, if you're needing a certain power at the start of a project and then ramping up, is it something where you would be able to do it in series or in parallel, multiple units? And then I guess my other question is, what is the timelines that you see when things will start to get to the commercial side where it's becoming more realistic in terms of having conversations?
Right. Okay, thanks. So the first question surrounding multiple units. It's very common in the nuclear world in Canada for having one site that has multiple generating units on it. So you know Pickering and the Bruce. There's a whole number of sites, and these multiple units are very attractive in the nuclear world. So this kind of concept isn't new in nuclear space to have multiple units at a site. And in fact, that is one of the advantages of picking maybe a smaller reactor size, is that you can grow your generating capacity as your demand grows over time. So yeah, so that's definitely a possibility. And sorry, what was the second half of the question? What was it again? I forgot. Right. Commercialization, right. So, yeah, so right now, a lot of the first demonstrations are lining up at the end of 2020, early 2030s. So I can't see how these will be commercialized until there's at least the first successful deployment. So I think, you know, in the 2030 timeframe is when the technology is really going to pick up.
Back here, what's the O&M look like for this? Do you have a nuclear engineer on every mine site if you've got remote deployments, or is it kind of a more remote management? How does that stack up?
Yeah, so I think a lot of these technology developers are looking at remote operation for some of it, but there's always going to be a need for on-site personnel. In terms of numbers, I'm not sure how many people are going to be needed on site. But in general, nuclear sites in Canada and around the world need some basic infrastructure and people at the sites. First and foremost in, you know, security, as well as maybe some for operation, and you know, fire department capabilities. These sorts of things are typical for nuclear sites. So I think they're targeting to have maybe more centralized operations, but I think there still will be a piece in there for local work.
Hi, I work for Finning Caterpillar, and you mentioned something about BEV vehicles being more loads per day to transport the material. Can you give me a little more clarification on that? Because that's certainly not the information that I'm receiving from Caterpillar.
Okay, so it depends on how you're accomplishing it, I guess. What we're assuming was the battery vehicles would be standalone. There would be no trolley assist or anything on site. So it kind of depends on what you're looking at in terms of infrastructure. I know there are trucks out there that will connect to overhead lines when they're going, you know, up a ramp, which helps with, you know, these sorts of efficiencies. So that's maybe part of it. The other part is that a lot of these vehicles are still in the early stages of development. So of course, the Caterpillar will be a lot closer to you know, the design of what these new trucks will look like. We kind of took the approach where we were assuming you know, a very similar sized truck. How much battery capacity do you put in there versus how much ore do you want to put in? So we kind of looked at it as a trade-off because the battery, in terms of battery size, is a weight problem in a lot of ways. So we kind of took that approach.
Let's talk, because your information is not as current as what I hear, so it might be worth having a discussion and getting you in touch with some of our senior technical people.
Right, that would be great. Yes, yeah. Please, let's have a discussion afterward. Okay, that looks like one more.
Given the, I guess, the potential for portability and maybe shorter term use of SMRs as compared with permanent plants, do you know if the regulator has considered how the costs of long-term waste management would be incorporated into the life cycle costs of an SMR?
Yeah, so generally the way it works in nuclear is you need to have a plan from start to finish before you get your license. So these sorts of things need to be thought of, the long-term waste management strategy. So I think there is a lot of work going on with the regulator to kind of figure out what the model is going to be for SMRs, because a lot of these technologies are quite different from the CANDU reactors they're used to licensing and dealing with. So I think it's going to be an evolution over time to see how the regulator can really manage this in a way that makes sense for small modular reactors. There's definitely no clear path right now on regulation for these, but that's something that's going to be building up in the coming years leading up to demonstrations.
Well, I see we're a bit over time, so I'd like to thank you, Travis Pettigrew, for this fascinating chat today. Thanks.
Thank you very
for
much.
joining.